In this video, we're going to do the proofs of the polynomial, the power rule, the product rule, and the quotient rule. And I hope you follow along with me and kind of do it with me as opposed to just watching. If you can understand the math behind how these work, then that will help you. And oftentimes teachers ask you to prove one of these on a test. So follow with me. Write it on a piece of paper if you can while we're going rather than just watching. And let's work this together. So let's start off with a constant. Now that's may not look like a polynomial, but you know constants are in polynomials. So if we're trying to do the derivative of a constant where we have f of x is equal to some number c, like f of x would be equal to 4 or y is equal to 4, something like that. Okay, now the definition of the derivative is the limit of f of x plus h minus f of x over h as h goes to 0. And remember, when we did these a long way, this is always h. There's nothing different about that, no matter what's going on with your function. This part down here is always your original function, so that would be c for us. And then this x plus h says everywhere you see an x plus h or an x, you should put an x plus h, and we don't have any x's. So there's no place to put an x plus h, so this is c plus no x's plus no x plus h's. So c minus c is 0, while h is still on its way to 0. So the 0 is going to win, so this is 0. Now, that's the proof. I want to sort of explain to you why it is 0. Remember that the derivative is the slope function, so that when you take the derivative, you're computing a function that would give you the slope anywhere along the curve. In this case, if you remember correctly, a y is equal to, say, 4 or 3 or 2 or negative 1 is a horizontal line. And it would be something like this. And a horizontal line has a slope of 0 throughout. No matter where it is, up or down on the axes, a horizontal line, the slope is 0. So I hope that sort of gives you a mental image as to why this function's derivative is 0. Now, let's move on. So we're going to say, what's the derivative of just x? Just a single x, okay? So the derivative, and I'm writing this over and over so that you will write it over and over and you'll memorize it, because invariably you're going to have to do one of these a long way. I would lay a bet that your teacher won't necessarily give that to you. I don't think they will. They might. Right. So let's talk about this. So when we do this, this bottom is always h. The part that's after this subtraction is always your original function. And for this part of f of x plus h, you go to the original function. Everywhere you see an x, you replace it with x plus h. So this is x plus h. And x plus h minus x is h. And anything over itself. So as you're getting closer and closer to 0, if you're at 0.1, it's 0.1 over 0.1. If you're at 0.001, it's 0.001 over 0.001, so it's 1. So the derivative is 1. And if you remember your graphing generalities, the y is equal to x line is actually a bisector of that quadrant. So this is 0, 0, 1, 1, 2, 2, negative 1, so forth. And the slope of this is 1. So you can see how these are all fitting together. If you had something like the function is equal to 2x, you would still do the derivative. And this would be 2 times the limit as h goes to 0 of f of x plus h minus f of x over h. So this is 2, and we've already said that this limit would be x, and this is x plus h. And we've already said that's 1, so this is 2 times 1, which is 2. And if you look here, and you have a y is equal to 2 x line, remember that you knew y is equal to mx plus b, where m is the slope, and so the slope is 2. Likewise, up here, if you have y is equal to x, the slope is 1, right? So I'm hoping this sort of kind of ties things together. Now, after we've done these two that are relatively straightforward, it takes a little bit of algebra that you actually may not have covered in your past classes. They don't necessarily talk in all the algebra classes about taking a binomial and expanding it past, like, say, a square or a cube. So there's general forms for how you do something like a plus b to the n, right? If we're familiar with something like x plus y squared, where it would be x squared plus 2xy plus y squared. And that we're comfortable with. But what happens when it's like x plus y to the 18th power, something like that, and have binomial expansion? Well, there's a pattern to it, and the beginnings of the pattern are in the one I just wrote down, so I want to talk to you about it just for a minute. So this coefficient is a 1. This coefficient is a 1. We kind of knew that, no surprise. But look at the powers on the terms. So this x is in the front, the y is in the back. So what happens? Look at the pattern. The x starts high because it's in the front. So it goes x squared, then you take 1 off the power, and then you have an x, and then you have no x's left, or you could think of it as x to the 0. So see how it goes 2, 1, 0. The y's in the back, so it starts high in the back, so you have y squared, take 1 off of it, take 1 more off, so technically you have y to the 0. Anything to the 0 power is 1. And the coefficients, these 1, 2, and 1, come from Pascal's triangle, which is this 1, 1, 1, and then you expand it with these ones on the outside. The terms in the middle come from adding the pieces above it. So you would add 1 and 1 is 2. So see, this is the 1, 2, 1. This number, the first number past the 1, tells you what your degree is, so the degree is 2. If you had another row, you'd have 1. Add the 1 and the 2 together, you get 3. 2 and 1 are 3. And then a 1, 1, 1 and 3 are 4. 3 and 3 are 6. 3 and 1 are 4, and 1. And so you could find these coefficients for a specific binomial. Now, we're not going to do a specific binomial. We are going to do a generic one with no numbers. Okay, so instead of using this triangle, we're going to have to use a different way, and I'm not going to explain it to you. This is something that would have come back up into algebra, and it takes a little bit. So you're just going to have to believe me on the coefficients, but I think you'll see the pattern. So what I'm trying to prove is that the derivative with respect to x of x to the n is n x to the n minus 1. That's actually what you're going to do, which says take the power, bring it down in front, multiply it, and take 1 off the original power. So our original function is x to the n. So I want to do the limit as h goes to 0 of f of x plus h minus f of x over h. That's the derivative. Now right here you're probably going, well, that's not a binomial. But this part right there is. All right. So if you have x plus h, because what we're going to do, this is always h. The back piece is always your original function, which for us is x to the n. The front piece is the original function where x is replaced with x plus h to the n. See the binomial? Sorry to say that n looks a lot like my h. All right, so here we go. So think of it this way. If you're going to expand that x plus h to the n, you would have x squared, oh, not x squared because we're not doing a square, x to the n. Then you would have x to the n minus 1, and then you would go x to the n minus 2, so that if n was 8, it would go 8, 7, 6, and then it would keep counting down until you get down here to x, to the first, and then you would have no x's. And then we're going to have minus x to the n all over h. So n, x, since it's in the front, counts down from n down to 0. H is in the back, so it's going to count down from the back to the front. Okay, so this is going to be h to the n, h to the n minus 1, and it's going to count up going this way, and this would be h squared, h, and then no h's. Now that you've seen these h to the zeros, I'm going to take those out. Now, I want you to notice that each one of these terms, the power adds up to n if you look at the 2. So here's a power of n. N minus 1 plus 1 is n. N minus 2 plus 2 is n. N minus 1 and an understood 1 make n, and this is n. So the powers, the degrees of these of the terms should all be a sum of n. All right, now how do we get the coefficients? So the lead one is n, is 1. Then this is n. This is n times n minus 1. If this looks sort of like if you did permutations and combinations and it talked about how many combinations you have, this should look kind of familiar. Okay, and then this would be n, and this would be 1. And that would be that. And all of this in here, it depends on how big your power is. If it's 18, 17, 104. So that just says I'm going to have the same pattern all the way down. So then what we're going to do is to say, well, look, hey, this x to the n is reduced to 0 with this minus x to the n. Remember when we did this, we were hoping that everything that was left had an h in common. So we are going to factor out that h. So that would be times n, x to the n minus 1 plus n times n minus 1 over 2, x to the n minus 2 times the remaining h plus some dots nx h to the n minus 2 plus h to the n minus 1. And you're like, where did the n minus 1 come from? I took an h out of there. Now these h's cancel. And you're left with the limit as h goes to 0 of, let me try to make that a little better, n x n minus 1 plus n times n minus 1 over 2 x to the n minus 2h plus n x h n minus 2 plus h of n minus h to the n minus 1. Now, each one of these terms has an h in it, so they're all going to go to 0, including all the ones that are in there. So all of those go to 0, and I'm left with n times x n minus 1. So there's that proof. All right, now we're going to do the product rule. And the product rule says if you have a function, some sort of function that's f of x times g of x, and you wanted to take the derivative of it, remember that it's the first times the derivative of the second plus the second times the derivative of the first. So if we have this, then y prime is the limit as h goes to 0. Here's my h. Here's my original function. Here's the one with x plus h in place of x. Can make that a little bit neater. All right. Now, the thing that we're going to do next is the key. Once you get this next part in there, then the rest of it just falls out with algebra and a little bit of preparation on your part as to what's going to be the next step, but the rest of it is just algebra. And it requires us to take a term that's not there, subtract it, and then add it back in. So basically it's like subtracting 2 and adding 2. It's like not adding any numbers at all. All right. And sometimes I've heard this called a fudge factor. So I'm going to spell it for you so you know what it is I'm saying. So let me spell it so you can actually see it. So it's Fudge, a fudge factor. Okay. Sometimes that's used for calculations and things when you're trying to explain some error that you anticipate, but I've also heard it referred to as things that you sort of use to make solutions you're trying to get to show up. All right. So the fudge factor that we're going to use is f of x plus h times g of x. And in the past, somewhere in the past, you can look this up in history, people uh, really enjoyed looking into math, and somebody came up with this and went, oh my goodness, if I effectively add this in and take it out, but we take it out first and then add it in, then I can make this proof work. So here is what they did. So you are going to take this limit as h goes to 0 and have this f of x plus h, g of x plus h. And you're going to take this term that's not actually there and subtract it because of the pattern that comes up, and then add it. If you add it first, the pattern's a little bit harder to see. I didn't leave enough space. It would still be algebraically correct if you added it in first and then subtracted it, but like I said, the pattern's a little bit more difficult to see. So this middle part right in here is something that you have to remember what the term is, and then you have to remember to subtract it and add it in. That's the part that you have to memorize out of this. You don't actually have to memorize the rest. You just really have to kind of understand it. So what we're going to do is, do you see that between here and here, there's an f plus f of f. I can do this. There's an f of x plus h in common. Sometimes it's really hard not to get all tongue tied up and try to say this. And do you see how between here and here there's a g of x in common? So between here and here there's a g of x in common. And between these front two terms there's an f of x plus h in common. And we're going to factor those out. So we have the limit as h goes to 0. of f of x plus h, right, times g of x plus h minus g of x. Now, doesn't that look like we're setting up for the derivative of g? And instead of leaving this h down here, I'm going to just put it here, remembering that this f of x plus h is really over 1. So I'm going to leave it out in front, group this together, plus the limit as h goes to 0. And remember, we're going to factor out that g of x. And that's going to leave me f of x plus h from the third term minus f of x from the fourth term over h. All right. Now, technically what you're going to do, I'm probably teaching you a bad habit. I don't actually make my students show this next step where they split this limit up between all of these pieces. I'll let them skip this step. But your teacher may not. So most likely, if they're going to have you do this as a proof, they've discussed proofs, maybe shown you one, so you can see how many steps they demonstrate. And if they put every single one of them in, you probably do too. Now, so, excuse me. So the limit as h goes to 0 of f of x plus h is just f of x. And the limit as h goes to 0 of g of x plus h minus g of x over h is the derivative of g. The limit of as h goes to 0 of g of x, well, there's no h to go to 0, so it's just g of x. And the limit as h goes to 0 of f of x plus h minus f of x over h is f prime of x. So the derivative with respect to x of f of x, g of x, is the first times the derivative of the second plus the second times the derivative of the first. Okay? One more to go. All right. So the quotient rule, the one my students always ask me not to ask, but sometimes I do. Because you are calculus students. You're tough. You have to keep saying that. I'm a calculus student. I'm tough. I can do this. Right now, what we're trying to prove is that it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. It helps if you kind of know your goal, all right, to get down there. So we have y is equal to f of x over g of x. And I'm going to try to take its derivative. So it's the limit as h goes to 0. And this is always your original function. And this is your original function with x replaced by x plus h. And if you can see, this is a complex fraction. So what do we do with complex fractions? We multiply by the least common denominator so we can clean it up a little bit. All right? Remember when we did limits with complex fractions? So the least common denominator, because h is over 1 and 1 goes into everything, is g of x times g of x plus h. So we're going to multiply top and bottom by that. Normally I write it down next to each piece so that we can cancel, but in order to kind of keep this a little cleaner, I'm going to not do that. Okay, so let's look at the bottom. H times g of x plus h is h. times g of x times g of x plus h, right? Now, up here, this g of x plus h is going to cancel this g of x plus h and leave us f of x plus h times g of x, okay? And then down here, this g of x times g of x plus h, the g of x's cancel and leave you f of x times g of x plus h. Okay, doing all right so far? And in that blank, we're going to put another fudge factor. Okay, keep in mind, I'm saying F-U-D-G-E, not something else. Okay, now, so we're going to put that in, and the fudge factor we're going to use in this one is not the same as before. It's this, right? We are going to subtract it and add it right in there. All right, so this is where I inserted that. All right. You doing okay so far? Now, what I'm going to try to do is to try to get an h up in the numerator and to get it to not be in the denominator. So some people can just say, okay, if this h is in the denominator, they can visualize it as being actually a denominator to the numerator, and some people cannot visualize that. So if you can visualize that this h is actually a denominator for the numerator, so I can actually sort of pull it into the numerator just by doing that, then I want to show you an alternative way to do it. And what you're going to do is to divide the top and the bottom by h. All right. And if you don't like that either, see how this results, and maybe you'll be able to visualize pulling that h up. So what I have is, if you look at this first term and the second term, these two, do you see how they have a g of x in common? So I'm going to have the g of x, and I'm going to get that h up with this one. So it'd be x plus h minus f of x, and pull the h up there, okay? Minus, and then you would have your f of x, you're going to factor out here, and you would have your g of x plus h minus g of x over h. And then you would have the h go away in the denominator. So then what you have is, as you take this limit to 0, and you just repeat this limit. This is one of the steps that, again, I let my students be able to skip, because you should know that the limit, when you take the limit of all of this, is actually taking the limit of all the pieces. But if your teacher wants you to write this down, this is what you're going to do. So in effect, you're just rewriting everything with the limit next to it. But like I said, some teachers will let you skip from here to here. It's your teacher that you have to decide. Now, as you walk through this, okay, the limit as h goes to 0 of g of x is just g of x. The limit as h goes to 0 of f of x plus h minus f of x over h is f prime minus the limit of f of x as h goes to 0 is f of x. The limit as h goes to 0 of g of x plus h minus g of x over h is g prime all over the limit of g of x plus h as h goes to 0 is g of x. The limit as h goes to 0 of g of x is g of x, and g of x times g of x is g of x squared. And there you go. The derivative of this, or the derivative with respect to x of that, is this part right here. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And I hope that helped. Like I said, the teachers sometimes put that on their test, but more importantly, I think it's really important that you understand as a student that these identities, these ideas that you are memorizing about the derivatives, that they are not just pulled out of thin air, that they actually have a reason as to why they work and that they were developed and that they were proven. So I hope this helps. Don't forget to like the video, subscribe to the channel if you haven't already, and we'll be moving on to doing other kinds of derivatives and what can you do with a derivative, and even later on during the video course you'll learn how to take an antiderivative. See you later.